This is the lesson for laws of logarithms. So first we're going to start with a review from Module 1. We know that the logarithm with base b is the inverse function. That's your blank there is inverse function. Of the exponential function with base b. So what we're saying, if we write this in exponential form, I can write b to the x is equal to y, where b, of course, is my base, x is the exponent, and then y is the answer. So again, this is in exponential form. So exponential. And then the inverse of that would be written as log base b of y is equal to x, where x is the exponential or the exponent in the exponential form, and then of course b again is the base. Now remember, we use inverse functions all the time. We just don't call them inverse functions. So if I ask you to solve an equation, something like 2x plus 4 equals 8, okay, well, to solve for x, the first thing I want to do is I want to subtract 4 from both sides. Well, so I'm reversing the addition of 4 by using its inverse, which is subtraction. So the inverse of addition is subtraction. So now I have 2x equals 4. So again, I'm solving for x. So you would divide by 2. Well, I'm reversing the multiplication by 2 with its inverse, which is division. So divide by 2. And so x is equal to 2. So just like addition and subtraction are inverse functions, multiplication and division are inverse functions, exponentials and logs are also inverse functions. And so that's going to come in really handy in the next module when we need to start solving for exponentials and for log equations. Well, if we have an exponential equation and we need to solve, we're going to use the log. If we have a log equation and we need to solve, we're going to use the exponential, okay? Just like we use addition to solve for subtraction and vice versa, and we use multiplication to offset or to as the inverse function of division and vice versa, okay? So keep that in mind. All right, so because of this relationship between the two, we know that the properties of exponents and logs are similar. They have corresponding properties that we can use. All right, so we've got some laws here of logs. Some of you guys had these in high school, and if not, if you did, this will be a refresher. If not, then we'll be learning them today. So 3 different rules that we're going to use that are for the laws of logs. We know that when we deal with the laws of logs that b, the base, has to be a positive number. I never have a base that is negative. I also never have a base that's 0. Okay, because 0 raised to any power, that doesn't make any sense. And then b can't also be 1. So why can't b be 1? Well, in exponential form, think about it this way. If I take 1 and I raise it to some power, maybe I take it and raise it to the 3rd power, it's still 1. If I take 1 and I raise it to the 17th power, it's still 1. So there's nothing that's exponential about that. Okay, remember logs and exponentials are related to each other. So the base will never be 1. And it has to be positive, something greater than 0. So base could be a fraction, could be a decimal, could be a whole number. Always has to be greater than 0, though. Okay, and then we're told that for these product rules down below, p is going to be a real number. That's going to be our power, actually. And then we're dealing with positive numbers a and b. So these are the properties of logs. We have what's called the product rule. So the product rule tells us that log base b of a times b is equal to the log base b of a plus the log base b of b. And what this allows us to do is it allows us to take a more complicated log or a larger log and break it into simpler pieces that are then easier to evaluate. Okay, the quotient rule, of course, quotient has to do with division. The quotient rule tells me that the log base b of a divided by b is the log base b of a minus the log base b of b. So notice the product rule, we use addition. The quotient rule, we use subtraction. Okay, so addition goes with the product rule, subtraction with the quotient rule. And finally then, the power rule tells me that the log base b of a raised to some power p can be rewritten as p times the log base b of a. And so like I said, this helps because we can take a really complicated log or a really large log and we can break it into more simplistic pieces, which are then easier to evaluate. So those are logs of any base, some base a, maybe log base 7, log base 14, log base 2, log base 10. Okay, so any base. Now we have corresponding rules that go with log base e, or the natural log. Okay, remember for log base e, we use the ln. Now you would never write log base e. Instead, what we write is the ln, and that means log base e. So don't write log base e. We'll write ln, and that's understood to be the log base e. Okay, so same thing. If I have the ln of a times b, that's the same as the ln of a plus the ln of b. The ln of a divided by b is the ln of a minus the ln of b, and the ln of a raised to the p power is p times the ln of a. So those are your laws of logs. You just sort of have to memorize those. If you don't know them already, just commit those to memory. From here, we have similar exponential properties that correspond with the rules or the laws that are listed above. Okay, so again, for exponential, we also have a product rule. My product rule of a raised to the u times a raised to the v. Now notice these are same base, okay, and you should know these. Okay, same base. So a raised to the u times a raised to the v is a raised to the u plus v. So for example, if I said, okay, what's 2 cubed times 2 raised to the 4th? Okay, well that would be 2 to the 7th. You just add 3 plus 4. Okay, quotient rule is a to the u divided by a to the v is equal to a, base a, raised to the u minus v. So similarly, if I did something like 2 to the 7th divided by 2 to the 5th, that could be simplified as 2 to the 2nd. 7 minus 5, of course, is 2. Okay, and then the power rule is a to the u times raised to the v power. That becomes a raised to the u times v. So if you had something like 2 to the 3rd raised to the 4th power, that would be 2 to the 12th power. So you can see this helps us to simplify our exponentials. Okay, so on page 2, we're going to take logs that are split up into 2 logs, and we're going to simplify it, or we're going to condense it into a single log, and that'll allow us to evaluate our answer. Okay, so I've got log base 4 of 8 plus log base 4 of 8. So I can use the product rule here from page 1. So this might be helpful if you can kind of flip back and forth. So I'll use the product rule, and the product rule tells me that with addition in between, this is the same as log base 4 of 8 times 8. So you think of 8 here as being a, and this one being b, and we know it's log base 4 of a times b, which of course 8 times 8 is 64. So log base 4 of 64. Well, to evaluate that, I just need to know that 4 raised to what power gives me 64. You can put this in your calculator if you need to. And 4 raised to the 3rd power is 64. 4 times 4 is 16, times 4 is 64. So the answer here is 3. Okay, so I took a log expression, log base 4 of 8 plus log base 4 of 8, and I was able to simplify it, and the answer is 3. Okay, now remember, these are equivalent expressions, just written in 2 different formats. Okay, for part B, log of 50 plus log of 2. Now the base is understood here to be base 10. So understood to be base 10 because it's not listed. Same rules still apply though, okay? So log base 10 of 50 plus log base 10 of 2. Again, this is product rule. So product rule. And this can be rewritten as the log of 50 times 2, which of course is the log of 100. Okay, remember this is base 10, so I need to know 10 raised to what power is 100, and the answer of course is 2. For C, the log of 5,000 minus the log of 50. Now this time, instead of having addition, I've got subtraction, so that tells me I'm going to use the quotient rule. This will be quotient rule. Okay, I can rewrite this as the log of 5,000 divided by 50, which of course is the log of 100. Okay, remember again, this is understood to be base 10, so I need to know 10 raised to what power is 100. The answer again is 2. Notice the answers are the same. Okay, so that means the log of 50 plus the log of 2 from part B is the same, is equal to the log of 5,000 minus the log of 50. Those are equivalent expressions because both of them simplify to an answer of 2. Okay, for D, log base 5 of 1 divided by x minus 3. Now this time I'm going to expand, again using the quotient rule. The other ones I condensed, okay, so I wrote them in a simpler format. This one I'm going to expand. So this will be log base 5 of 1 minus log base 5 of x minus 3. And we don't do anything to separate the x minus 3. There are no laws of logs for that. Okay, so I can further evaluate log base 5 of 1. I need to know 5 raised to what power is 1? Well, I know that any number raised to the 0 power is 1, so that means 5 raised to the 0 power is 1, so this is actually 0. Minus log base 5 of x minus 3 is fully simplified, fully expanded, so the answer is negative log base 5 of x minus 3. Okay, now make yourself a note here. Okay, there are no log rules, or I shouldn't say log rules. There are no laws of logs for sums or differences, for a sum or difference. Okay. So that's a common mistake. People want to take that log base 5 of x minus 3 and then split it into 2 different logs. You can't do that. The product rule tells me if this said x times 3, you could split it into with addition. And the quotient rule told me if it said x divided by 3, that you could split it using subtraction. But there are no laws of logs for sum or difference, okay, within the log. All right, so next one. For the following, we're going to fully expand each log expression. So the first one is the log base 7 of 49xy, okay? So that's 49 times x times y. So I'm going to use the product rule here to fully expand. So this will be equal to log base 7 of 49 plus log base 7 of x plus log base 7 of y. And then I can further simplify log base 7 of 49. Well, 7 squared would equal 49, so that's equal to 2 plus log base 7 of x plus log base 7 of y. And that is your final answer. Okay, number 2, log base 5 of the square root of x squared plus 1. So for this one, I'm actually going to use the power rule. We haven't used that yet. Okay, this can be rewritten as log base 5 of x squared plus 1 raised to the 1/2, because remember the square root is the same as the power of 1/2. So now power rule tells me I can bring that exponent down front. So this is 1/2 the log base 5 of x squared plus 1. And again, I'm done. There are no rules for sum or differences. So again, that cannot be split apart. This is fully expanded at this point. Okay, for number 3, we're taking the ln of a squared times the square root of b divided by 3c to the 4th. So the first thing you want to do is anytime you have a radical, you want to rewrite that as an exponent. So this will be the ln of a squared times b to the 1/2, because I know the square root of b is the same as b to the 1/2, divided by 3c to the 4th. Now, we're going to use some combination here of the power rule, the product rule, and the quotient rule, all 3 of them. Okay, so first thing I'm going to do is I'm going to use the product rule for what's in the numerator. Okay, so I know I've got a squared times b to the 1/2. So product rule tells me I can rewrite them with addition. So this will be the ln of a squared plus the ln of b to the 1/2. All I did was use the product rule for the numerator and I split them. Now, here's a little trick. Everything that's in the numerator is positive. So this is positive, this is positive. Now, when I apply the quotient rule, remember quotient rule tells me that the ln of a divided by b is equal to the ln of a minus the ln of b. So everything that's in the denominator has a negative in front of it, okay? So I'll rewrite what's in the denominator using subtraction. So this will be minus the ln of 3 minus the ln of c to the 4th. And now it's easy to see. So everything positive I know belongs to the numerator. Everything negative is from the denominator, okay? And if you split it that way, then it's just easy. Sometimes people use a bunch of parentheses and then you have to distribute and it just gets really messy. This is just a much easier way. If you follow this rule, it works every single time. Okay, so now I'm still not done. I have to use the power rule to bring those powers down front. So the power of 2 goes in the front, so 2 times the ln of a plus 1/2 times the ln of b minus the ln of 3 minus 4 times the ln of c. Okay, you can put parentheses around these if you want to. Okay, sometimes it's necessary. These I could have used the parentheses or not because it was obvious what I was taking the ln of. Okay, and so that is your answer, fully expanded. One note here, the ln of 3. You could put this in your calculator and come up with a decimal answer, but you don't want to do that because your decimal answer is not as exact as just leaving it as negative the ln of 3. So unless you can evaluate it to an exact value, like when we had log base 10 of 100 and that equaled 2, that you would want to simplify. But something like negative the ln of 3, that's going to give you a decimal, and so it's more exact to leave it as negative the ln of 3, so that's what we're going to do. Okay, so number 4 says log base 2 of x times x squared plus 1 divided by the square root of x squared minus 1. So again, we're going to rewrite it, getting rid of the radicals. So this will be log base 2 of x times x squared plus 1 divided by x squared minus 1 raised to the 1/2. So I want to make sure that everything is fully factored before I do my expansion. It'll just make life easier. So I'm not quite done here with factoring. So log base 2, this will be x times x squared plus 1. That does not expand any further. Divided by x squared minus 1 actually can be factored further to x minus 1 times x plus 1. Don't forget, this whole thing is raised to the 1/2. So that can be rewritten as log base 2 of x times x squared plus 1 divided by x minus 1 times x plus 1. The whole thing raised to the 1/2 is the same as x minus 1 to the 1/2 times x plus 1 to the 1/2. Okay, now everything is fully factored, so now I'm ready to expand. So I have, remember, everything is positive, everything in the denominator will be negative. So log base 2 of x plus, you can use parentheses, log base 2 of x squared plus 1. So that's the expansion of the numerator. Now everything in the denominator is negative, minus log base 2 of x minus 1 to the 1/2 minus log base 2 of x plus 1 to the 1/2. Almost done. Last thing I need to do is I'm going to use the power rule to bring all of the exponents down front. So this is log base 2 of x plus log base 2. Remember, there are no rules for addition and subtraction, so this just remains x squared plus 1 minus, now bring the power down front, 1/2 log base 2 of x minus 1 minus 1/2 log base 2 of x plus 1. And there is your log fully expanded. So we can go both directions. We can fully expand or we can fully condense. So these were full expansions. Okay, you start with a single log and you fully expanded. So we took a single log and expanded it into 1, 2, 3, 4 terms. Okay, and then what we're getting ready to do now is we're going to take multiple terms and condense into a single log. Okay, so Number one, we're supposed to condense the following into one logarithmic expression. So I've got log base 2 of A minus log base 2 of B plus 2 times log base 2 of C. So first thing I'm going to do is I'm going to use the power rule. So the power rule to move the values in front of the log back to exponents. So this will be rewritten. This will remain log base 2 of A minus log base 2 of B, and the 2, the power in front, will, or the value in front, will become a power. So plus log base 2 of C squared. Okay, and then now I'm ready to condense further. Now remember, anything with an addition, anything that's positive, so this is understood to be positive, this of course is positive, will go in the numerator. Anything that's negative goes in the denominator. Okay, so log base 2, everything is log base 2. That's the other important thing to remember here too. If all the values, all your terms are not the same base, you cannot combine them. Okay, so everything has to be the same base. So don't just jump in and assume you can start combining different bases. That's not allowed. So everything has to be the same base. Okay, so now using the product rule, and we'll use the quotient rule together here. Okay, again, if it's positive, it goes in the numerator. So log base 2, positive A goes in the numerator, negative log base 2 of B, so B goes in the denominator, positive log base 2 of C squared goes in the numerator. So as a single expression, that is log base 2 of A times C squared divided by B. And if you have a second on a test or a homework, then work from here and expand it and see if you get the original problem. Okay, if you've done everything correctly, obviously you will. All right, so number 2. 2 times log base 5 of x plus 2 log base 5 of y minus 3 log base 5 of z. Okay, so this is one I would probably have you do in class on your own. So pause here and work through it and then come back and see if you get the right answer. Okay, so first thing we want to do is we actually want to distribute the 2. So this will be 2 log base 5 of x plus 4 log base 5 of y minus 6 log base 5 of z. Again, they're all log base 5, which means they can be condensed, okay? I'm going to use the power rule first, which is all the numbers out front are going to become powers. So this will be log base 5 of x squared plus log base 5 of y to the 4th minus log base 5 of z to the 6th. And now I'm ready to use the product rule and the quotient rule. If it's positive, it goes in the numerator. If it's negative, it goes in the denominator. So log base 5 x squared times y to the 4th divided by z to the 6th. And so at that point, I'm done. Now, you may have done this a different way. You may have worked this differently. Another answer you could have gotten, which is equivalent and would be completely fine, is log base 5 of x times y squared divided by z cubed, all of that raised to the 2nd power. And that would be fine. These are equivalent because I could take x here, raise it to the 2nd power, I'd get x squared. Take y squared, raise it to the 2nd power, I'd get y to the 4th. Z cubed, 2nd power would give me z to the 6th, okay? So depending on which way you come at this, either one of these answers is correct. Okay, so change of base formula used to be something that was really important when we were dealing with scientific calculators. Your calculator, if you have the TI-36, actually has the ability to find or to evaluate logs of all different sorts of bases. If you pull out your calculator and look at the LN log button, which is the button right under the blue 2nd key in the top left corner, if you push that button once, it says LN. If you push it a 2nd time, it says log. If you push it a 3rd time, you can type in any base and do an evaluation, okay? If you don't have a TI-36 and so you don't have the ability to do that, you're going to use change of base formula. It's very simple, and it's just good to know too in case you were somewhere maybe all you had was your phone and you needed to do an evaluation, you wouldn't have the ability to type in different bases. So it's really very easy. Okay, so it says most calculators only have two types of log keys, one for the common log, which is base 10, and one for natural log, base E. Okay, and so those are obviously the most common. Those are the ones you're going to use most often, but sometimes you need to evaluate a log that's in some other base. So if I gave you something like log base 7 of 43, okay, you might need to evaluate that. And so we could do that in the TI-36. You just hit that log button 3 times and you would type it in and it would give the answer, okay? But if you don't have the ability to do that, you have a different calculator, we're going to use the change of base formula to change the base. So this, your notes here, use the change of base formula. Okay, so in that instance, we're told that A, B, and X are going to be positive real numbers. A will not equal 1, and B will not equal 1. And then the log base A of X can be converted to some other base B. Okay, so log base A of X is going to equal log base B of X divided by log base B of A. Okay. Okay, so this is what we know. Base 10, then log base A of X is going to equal log of X divided by log of A, okay? If I'm using base E, then log base A of X would equal the ln of X divided by the ln of A. So whatever the base is what goes in the bottom in the denominator, and then we just find the ln in this case for the numerator. So for my example above, log base 7 of 43, if I were using change of base formula, that would be the same as the log of 43 divided by the log of 7. And for both of these, the base is understood to be base 10, okay? Every calculator has the ability to do a base 10, okay? So anytime you have to find a base that's something other than 10 or something other than E, we'll just use the change of base formula unless you have a TI-36, and then you're just going to type it in. You're not going to worry about it, okay? So let's do one more example. So if I asked you to evaluate log base 2 of 12 using the change of base formula, then log base 2 of 12 would equal the log of 12, and all I'm doing is using base 10 divided by the log of 2. So if you put that in your calculator, you will get 3.585, okay? Now you don't have to use base 10. I could have just as easily done ln of 12 divided by the ln of 2. Well, guess what? Type that into your calculator, you get the same answer. So whether you use ln or whether you use log base 10, you'll get the same answer. And both of those represent the log base 2 of 12. Okay, so let's talk through some common mistakes quick that students make all the time so that hopefully you won't make those mistakes. All right, so the first one is that they will tell me that the log base A of X plus Y is equal to the log base A of X plus the log base A of Y. Now remember, we already talked about there are no log rules, no laws of logs for addition and subtraction within the problem. Okay. Okay, and actually what we know is that log base A of X plus log base A of Y is actually equal to the log base A of X times Y. Okay, so it is not log base A of X plus Y. All right, another one that we see all the time, log base A divided by log base B. People will tell me that that's equal to the log of A divided by B. Okay, which, I mean, these aren't crazy jumps to make, it's just not true. Okay, and what we actually know is log of A divided by log of B, if you expanded that, is log of A minus log of B, not this. Okay, and then the third one is that log base 2 of X, that entire quantity cubed, is equal to 3 times log base 2 of X. That's not true. Okay, in fact, 3 times log base 2 of X is actually equal to log base 2 of X cubed. So only the x value is cubed, not the entire quantity. So this, again, is also not true, okay? In fact, log base 2 of x cubed, if I asked you to expand that, is actually log base 2 of x times log base 2 of x times log base 2 of x 3 times. So very, very different than log base 2 of x cubed, okay? So just some common mistakes, be on the lookout for those. Really the main thing is if you know your laws of logs backwards and forwards, then you're less likely to make those common mistakes. Okay, for page 5, if we were in class, I would have you do all 5 of these on your own. All you're going to do for the first 3 is you're going to fully expand each expression, and then for the last 2, you're going to fully condense into a single log expression. So pause the video, work all 3 of these, and then come back and do a quick check to make sure your work is correct. Okay, so for this one, first thing I want to do is get rid of the radical. So the ln, this will be x cubed divided by 2y to the 5th. The entire quantity raised to the 1/2. So that's the ln of x cubed to the 1/2. So 3 times 1/2 is x to the 3/2 divided by, remember, each of these quantities is to the 1/2. So this is 2 to the 1/2. Y, 5 times 1/2 is 5/2. And then from here, you just expand, numerator is positive. So this becomes the ln of x to the 3/2. Anything in the denominator is negative, minus the ln of 2 to the 1/2, minus the ln of y to the 5/2. Let's write this in parentheses so it's obvious. And then finally, we're going to bring the powers out front. And that is fully expanded. Okay, number 2, log base 4, same thing. I've got square roots here, so I'm going to get rid of that, rewrite that as a power. So this is log of the, actually not a square root, a 4th root. So that's the log of x squared plus y squared to the 1/4. Okay. That cannot be split. X squared plus y squared cannot be split apart. So you can keep those together. So this is 1/4 the log of x squared plus y squared. Number 3, if it's in the numerator, it's positive. So log base 2 of 3 plus log base 2 of x squared minus log base 2 of x minus 2 to the 4th. And then bring the powers out front. So log base 2 of 3 plus 2 times log base 2 of x minus 4 times log base 2 of x minus 2. Now you'll notice this, I put parentheses around the x minus 2, but I didn't put parentheses around the x. You definitely need parentheses around the x minus 2 because you want it to be obvious that you're taking the log base 2 of x minus 2, not just the log base 2 of x and then subtracting 2. So it's probably good form for you guys to just put parentheses around everything that you're taking the log of, just so that it's super clear and you don't have to worry about making that mistake. Condense into a single expression. You always want to use the power rule first. This is the ln of 5 plus the ln of x squared plus the ln of x squared plus 5 cubed. And then now we're going to use the product rule. They're all positive, so we'll condense into a single expression. The ln of 5x squared times x squared plus 5 cubed. And so be careful here. Make sure you use brackets or parentheses because we want to know we're taking the ln of that entire expression. Last one, we're looking at 4 times the log of x minus 1/3 the log of x squared plus 1 plus 2 times the log of x minus 1. Power rule is always first. So log of x to the 4th minus the log of x squared plus 1 to the 1/3 plus the log of x minus 1 squared, and then now use the product rule and the quotient rule. Remember, if it's positive, it goes in the numerator, negative in the denominator. So this is the log of x to the fourth minus the log of x squared plus 1 to the 1/3. So minus tells me this goes in the numerator, x squared, sorry, denominator, x squared plus 1 to the 1/3, and then the log of x minus 1 squared is x minus 1 squared in the numerator. And so your final answer is you're taking the log of x to the fourth times x minus 1 squared times x squared plus 1 to the 1/3. If you want to convert that to a radical, it's log x to the fourth times x minus 1 squared divided by the cubed root of x squared plus 1. Make sure you put parentheses around the entire expression.